All right, so in the last video, we talked about how enzymes work by lowering the energy of activation. In doing so, they lower that barrier of energy that reactants have to get over in order to go on to the products. And this is what's normally might be preventing an exergonic reaction from happening automatically and immediately, right? Or preventing our sugar from spontaneously combusting, or a tree from bursting into flames without something putting a little bit of energy to get over that energy of activation. So how does the cell, or how does the enzyme lower the energy of activation? There's a few options, right? Oh, sorry. So this is what that would look like. So if this is our normal reaction, there's the normal energy of activation in red. This is the catalyzed reaction with the energy of activation lowered. And again, you can see that the energy of the reactants, the energy of the products, that doesn't change. So the delta G does not change. We're just lowering the energy of activation, thus allowing the reaction to happen more quickly because now more molecules have enough energy and ability to get over. All right, so how does this happen? Well, some of the mechanisms. The first one I like to call the nuts and bolts analogy. So if I have some nuts and bolts, right? So I have the nut and the bolt. We know that these fit perfectly, right? And we're going to talk more about the active site for an enzyme that the substrate binds in next, but it's perfectly fit, right? Fold equals function. But that does not mean that these are going to spontaneously screw themselves together. So even if I took this and shook it around or whatever, I really don't expect the nut to kind of wheel its way around the bolt. That's because there's a little bit of energy needed in order to get that perfect fit to bring them together, to make that happen, right? And that's true also for a reaction. If I needed two of these reactants to react and create a bond and come together, right? So maybe I'm creating a dehydration reaction, I'm linking amino acids together. Well, the likelihood of those two things coming together in the perfect orientation for them to link without any help is very, very low. So basically what the enzyme is doing is kind of helping maintain that orientation, helping bring them together. So you can almost think of an enzyme as having two binding pockets that perfectly bring the two reactants, the substrates, together so that they can react, right? So the nuts and bolts analogy, and there is energy involved and time involved. If we had to wait for these things to diffuse and just randomly bump into each other in the cell, that would take a long time, and that diffusion kind of requires some energy and movement. So bringing it together lowers that energy of activation. Now the reaction can happen, and maybe it's exergonic or whatever. We also talked about that transition state being a intermediate state where the bonds are stressed and there's a higher energy involved. So maybe there's some charges in there. Well, if there's some charges in there, enzymes can stabilize that. So the enzyme might have some charge that's perfectly oriented to be opposite these charges. Or maybe in breaking that reaction, I have to take a hydrophobic residue and expose it to water for a little bit. Well, the enzyme might have a hydrophobic region that helps kind of block that exposure to water while it's reacting. That lowers the energy. So one of the things that an enzyme can do, in addition to the nuts and bolts bringing things together, is it can stabilize that transition state en route from reactants to products. And then sometimes a reaction is like breaking a bond. So actually there would be energy, believe it or not, a little bit of heat created if I break this pencil, because I'm creating disorder, creating entropy, right? But there's some strength in this. And so my hands would have to be like the enzyme, creating that stress, and then put enough stress, and then that bond will break. And so that's the last one down here, where something can bind to the enzyme, and then when it binds to the enzyme, that causes the enzyme to change conformation, which basically stresses the bond and helps it break. Right? So these are the three major ways that an enzyme can lower that energy of activation, helping bring things together to react in the right orientation, stabilizing that intermediate transition state, and then kind of once it binds, creating stress in the reactants to maybe help it break if the reactants are breaking a bond to become the products. Excuse me. All right. So ultimately, all of this is going to help stabilize this transition state. So maybe the energy is just needed because it takes a long time and it's pretty random for these two to interact with each other. So nuts and bolts bring them together. Stabilize some energetically unfavorable intermediates, make them less unfavorable. That would lower the energy of activation. Or stress it, So if you're breaking a bond, that stress is going to kind of help you reach from this point to this point more easily. All right, so there's the properties of enzymes so far. Usually proteins, sometimes RNA. We talked a ton about how they speed up the chemical reaction by lowering the energy of activation, and now we've talked a little bit about the mechanism by which that can happen. Right? By doing this, this is the main purpose of enzymes. They allow reactions to occur at physiological temperatures, pressure, pH, and low concentrations. Right? So what I mean by this is if we needed a reaction to occur, in chemistry, we could heat it up and give those reactants more energy, and that'll help them get over the energy of activation. We could also add pressure to kind of force reactants together and help them force them to react. Right? You can alter pH, but you can't do this in a cell. The other thing you could do is just have so many reactants that they're automatically going to run into each other, and some of the reactions will occur. Right? If you have more reactants, then you have more chance of some of those reactants having enough energy. But you can't do this in a cell. The cell has to do this at physiological temperature, pressure, pH, and low concentrations. And what I mean by physiological means life relevant, right? I need to do this at 37 degrees Celsius or 98.6 Fahrenheit body temperature. I need to do this at normal atmospheric pressure, right? I can't put myself in a hyperbolic chamber. And I need to do this with normal pH. And I can't load my cells up with high concentrations of everything I need to react, so it has to be relatively low. And so an only way to do this at physiological conditions to speed it up is lowering the energy of activation. Okay. We've talked a lot about this, but I want to stress it. Do not be the person that on an exam says enzymes can change delta G. Enzymes do not change the thermodynamics. They do not change delta G. They don't change the energy of the reactants. They don't change the energy of the products. They just lower the energy of activation along the way. And so here's where I want us to practice a little bit again. So pretend this is in class. This means this is important. I want you to get out a sheet of paper and basically draw 4 diagrams like this, where we have our energy levels on the y-axis, the reaction proceeding like we've seen before on the x-axis. And I want you to draw a diagram of a non-spontaneous reaction, so in other words, an endergonic reaction. Another one of a spontaneous reaction that's exergonic that would occur instantaneously without the addition of any energy. A spontaneous reaction that's kinetically stable, and the catalyzed version of the same reaction drawn in C. So pause the video for a moment and see if you can draw those out. Try the best you can. Look a couple things up if you need to. We're going to talk about them more in a second, but practice this. This is important. All right, so hopefully you've got the things that you drew and practiced with. And so here I have 4 options. So these are the ones I would have drawn, but not necessarily in this order. So I want you to take a look at yours and try to match it. So which one of these would be a non-spontaneous endergonic reaction? So 1, 2, 3, or 4. Which of those options would represent the endergonic non-spontaneous reaction? Well, that would be number 4, right? Endergonic means it's uphill. And just because it's uphill doesn't mean it also wouldn't have an energy of activation, right? So the energy of activation would be this little bit right here. The delta G would still be the difference in products and reactants, but that is a positive delta G. The products have more energy than the reactants. More minus less is a positive number. This would be an endergonic non-spontaneous reaction. It's uphill, right? So next, what about a spontaneous reaction that's exergonic that would instantaneously occur without the addition of any energy? Would that be 1, 2, 3, or 4? Well, a spontaneous reaction that's instantaneous would be exergonic, downhill, that would be 1, and wouldn't have an energy of activation. So basically, these are just that boulder is going to automatically roll down the hill. There's no energy it has to get over. This would be the type of thing that would be almost like the most unstable explosive or something like that. There doesn't need much to set it off or anything at all. So this would be not only spontaneous, a la exergonic, but also instantaneous. There's no energy of activation. All right, so how about a spontaneous reaction that's kinetically stable? 1, 2, 3, or 4? Well, that would be 3 here. So we can see the reactants products. This is a negative delta G, that's spontaneous, but there's a really large energy of activation here. That means that it's not going to roll from here to here very easily. That's the kinetically stable. This is like my sugar that isn't going to explode and so forth. So that energy of activation makes this stable even though it's a spontaneous exergonic reaction. And so if a cell wanted that to occur, the cell would catalyze that reaction, D. All right, so what's the catalyzed version of the reaction? Well, the catalyzed version would be up here in 2. So assume this dotted line is the original non-catalyzed reaction, the solid green line would be the catalyzed version, right? And again, remember, it does not change the energy of the reactants, does not change the energy of the products, therefore it doesn't change the delta G, it just lowers that energy of your reaction, helping it occur more quickly and at physiologically relevant temperature and pH and pressure, etc. All right, so again, just kind of showing this through. The enzyme lowers the energy of activation, but changes nothing else. Delta G did not change. It can't take an endergonic reaction and make it exergonic. We learned in class a few ways that a cell can help an endergonic reaction occur. Enzymes is not one of those ways. An enzyme cannot take something with a positive delta G and make it a negative delta G. All it can do is lower the energy of activation. Now, that doesn't mean it can't help speed up an endergonic reaction. So here's the lowering the energy of activation of my exergonic reaction. An endergonic reaction can still have an energy of activation on its way from reactants to products. And an enzyme can lower that and help speed that up. But there still needs to be an input of energy to get over this positive delta G. Because by lowering this energy of activation, I still have not changed the energy of the reactants or the products. Delta G is the same, energy of activation is lower. So an enzyme can help speed it up, but it can't make an endergonic reaction. For an endergonic reaction, you still need that input of energy. So again, can't stress enough, an enzyme lowers the energy of activation, does not change the thermodynamics delta G. All right, another thing to remember about an enzyme is it's not changed or used up by the reaction. Right, so it's a catalyst, and the definition of a catalyst is that it speeds up reactions without being used in the reaction. So if we take a look here, here's an enzyme. This would be an enzyme building something, right? So this is an anabolic reaction. It's taking two substrates, helping link them together. So this would be the active site where they're binding, and it fits them both, and then it releases them. But once it releases them, that enzyme's ready to bind another one, right? So an enzyme can do this reaction, then do it again, then do it again. It's not a part of the reaction. It just helps the reaction along. Here's one that's helping break a bond. So it's going to bind that, stress that bond, and release it, but then it's available to bind again, so it can keep doing that thing. Right? And most cellular events are basically at a long metabolic path where you have multiple events. So one enzyme is going to help take reactant A and make it B. A second enzyme will take B and make it C. A third one will take C and make it D. And along the way, we start with one thing and the body ends with something else that it needs. All right, so that's the end of this second one. There'll be one more, and then hopefully all of this is starting to make sense. Bring questions to class.